All right, so we're into section 10.5 now. And before we start on today's topic, I just wanted to do a quick recap of what we talked about yesterday, just because we had to go so quickly, and kind of make a point. If we had completed the problem, the example, I would have gotten to this, but since we didn't, I want to make sure that we understand. So, yesterday we said that when we're in polar coordinates, that the slope dy dx equals, just like we talked about with other parametric equations, dy d theta over dx d theta. And we wrote this out explicitly using polar coordinates to come up with an expression, a kind of complicated looking expression for the slope that involves f of theta and sines and cosines. And the point of doing that was, and before I say that, just another quick reminder that the slope does not equal dr d theta. The reason that we wrote out this explicit formula was that we saw if at the pole, if r equals 0, we have a convenient way of finding the slope of the tangent line. If r equals 0 and r prime not equal 0, then dy dx turns out just to be tangent theta for whatever angle gives us r equals 0. So one reason we do this is because this gives us a convenient way to find the slope at find the tangent at the pole. Sometimes we might be interested in the tangent at the pole. We did an example yesterday. We looked at our example was r equals 2 plus 2 cosine theta. In this example, we found a candidate for the tangent at the pole where theta is pi. And after we fixed my mistake, we realized that dr d theta was actually 0 there. And if we look at that graph, this is a cardioid, we have a cusp at the pole. So we couldn't find a tangent at the pole. When we went through our finding the horizontal and vertical tangents, we would find that theta equals pi is a candidate for a horizontal tangent, and theta equals pi is a candidate for a vertical tangent. So if we hadn't looked at this, if we hadn't looked at the pole, we would get theta equals pi as a possibility for where we have a vertical tangent and a horizontal tangent. So if we hadn't examined what happens here when r equals 0, we would have that theta equals pi for a possibility for either a vertical or a horizontal tangent. So sometimes when we have a graph that has a cusp, sometimes depending on the behavior of the graph, we can get candidates for theta for a point of vertical or horizontal tangency that don't actually give us a vertical or horizontal tangent. So that's why sometimes we need to look at the tangent at the pole because it can clear up those kinds of situations where we might not be sure what exactly is going on. And if we would have finished this example, we would have seen that theta equals pi comes out in each of those for dy d theta equals 0 and dx d theta equals 0. So we needed to make sure that we understood what was going on there with theta equals pi. So that's two reasons that we wrote our explicit equation for dy dx. One, it gives us an easy way to find the tangent at the pole, and two, it gives us a way to analyze points where it might not be clear just from our work what exactly is going on. All right. So that was the main point of what we did yesterday. So let's move on to area, finding area. So we're going to use sectors of circles to find area in polar coordinates. So we need to remember that the area of a sector of a circle is A equals 1/2 r squared theta, where r is the radius of our circle and theta is our central angle. Now if we have a function, if r is some function of theta, so our radius varies as we move around, and we want to find the area between theta equals alpha and theta equals beta. We're going to divide our region into subintervals and add the area of each small sector. So what we're looking at is, here are, and we've done this, we've used this argument pretty much any time we've done anything with integration, when we're trying to add things up. This is my pi over 2, and this is 0. So here's my graph of my polar equation, and we're looking at the area in this little section. So we move through an angle delta theta, and this is theta equals alpha and theta equals beta up here. And at theta equals alpha we have some radius r sub I. So we're going to add the areas of these little sectors, and we're going to say delta theta is very small. So the area of this little sector is approximately the area of the section is approximately the sum for I equals 1 to n. We're dividing it into n intervals of 1/2 f of theta sub I, that's r sub I, squared, times delta theta sub I.
What is it? In from what to, or starting at, let's say I equals 1 on the bottom?
Yes, I equals 1 to n. So we're just dividing this into to n subintervals, and the area of the ith subinterval is r sub I squared times delta theta sub I divided by 2. And we're adding all those the areas of those little sectors up. So our area is approximately this sum. If we take the limit as delta theta gets very, very small, so we're looking at really, really tiny sectors, we get an integral. So in the limit, as delta theta gets smaller and smaller, we get our area is the 1/2 the integral from alpha to beta of f of theta squared d theta. And we want f to be continuous on our interval, and we want a radius to be non-negative. We want a radius to be positive. And we can rewrite this just to be more consistent with our notation. We would say this is 1/2 integral from alpha to beta of r squared d theta is normally how we would write this. Linda, I think I have to give you the math box key. Yeah, okay, great. So this is our expression. This is how we find the area of a polar that's inside some kind of polar curve. Questions on our development? Pretty straightforward. Something that we should be relatively familiar with. So let's look at a couple of examples, and then we'll go a little further with this, and then we'll talk about a place where we have to be careful. All right. So we want to find the area of one petal of r equals 3 cosine 3 theta. So this gives us a rose curve. And I have a nice sketch of it here. Let me grab that. So there's our graph. Nice rose curve. So to find this area, we have our graph is symmetrical. So we're just going to look at one petal, and then we'll find the area that's inside one petal. Actually, I was thinking it asks us for the whole thing. So it just asks us for the area of one petal. So let's look at the right petal just to make it easier on ourselves. R equals 0. So we're here at the pole. We need to find our limits of integration. So r equals 0 when 3 cosine 3 theta equals 0. I think this was didn't we just talk about this on our homework? So 3 theta equals pi over 2. So theta equals pi over 6. So that's the first time that theta equals 0. We can see that if this angle is pi over 6, we could look at other values of theta that give us where 3 cosine 3 theta is 0. Or we can look at our graph and say, okay, if positive pi over 6 is where theta equals 0, it's symmetrical, so negative pi over 6 is going to give us theta equals 0 also. So I'm here at pi over 6, and I'm also here at negative pi over 6. You can go through it analytically and find the other points, or we can just kind of be clever and look at our graph and say that since it's symmetrical, theta equals negative pi over 6 will also give r equals 0. And this is a nice one because it leads to a trig identity that is a good one to start working on memorizing because it comes up a lot in integrals of trig functions. So our area of this petal is going to be 1/2 the integral from minus pi over 6 to pi over 6 of our radius 3 cosine 3 theta squared d theta. And that equals 9/2 our integral of cosine squared 3 theta. So this integral cosine squared 3 theta, we can't do a u substitution because we don't have a du. But we have a very nice trig identity. Cosine squared 3 theta equals 1 plus cosine 6 theta over 2. So we have
That one.
this is called a power reducing formula. When we have cosine squared theta comes up a lot in trig integrals. So we need to remember this identity, this power reducing identity. What's that?
It's a manipulation of the formulas for cosine 2 theta, right?
Right, right. So this gives us just the first power of cosine of 6 theta, which is much easier to integrate. So we end up with 9/2 integral from minus pi over 6 to pi over 6, 1 plus cosine 6 theta over 2 d theta. And then we can separate this into two integrals, and we end up with this equals 9/4 theta plus 1/6 sine of 6 theta, and we're evaluating that on minus pi over 6 to pi over 6. What's that?
Oh, no, because you have mine. Oh, backwards, right?
Yeah, I think we're good. And when we evaluate this, this comes out to 3 pi over 4. And if we had evaluated our integral, if instead of using negative pi over 6, we could use 11 pi over 6 and evaluate our integral from 11 pi over 6 to pi over 6, which would give us this pedal, we would come up with the same answer.
Wouldn't that make it go backwards? Like 11 pi over 6 going to pi over 6? Wouldn't that do some weird things to go something farther along the graph? Something
Well, the cosine of 11 pi over 6 or the sine of 11 pi over 6, I guess we would get, it would be negative, but we have it should all work out.
Okay.
It should all work out no matter how you pick your limits.
Okay.
So often when we're finding areas with polar graphs, finding the limits of integration is the challenge. Let's see. Do I want to do that one? I think we're okay on. I think that's good.
How would you know when you're going that it traces that it starts with pi or it starts with negative pi?
So we could look at theta. So we could say when theta equals 0, cosine of 3 theta. So we just end up with 3. When theta equals 0, we're at r equals 3, and then we came up with our first limit, theta equals pi over 6. So it goes to 0. So we're starting our graph here, and at theta equals pi over 6, we're at 0. So we know we go around this way. So our graph this graph would actually be traced along like so, and then we'd be at negative pi over 6 here. So we'd be going that way. So that would take us around that way. That's usually how I do it if I'm not sure. I just start plugging in some points. Theta equals 0, r equals this, theta equals whatever we're interested in, and it goes there just to make sure that I'm getting the parts of it that I want to. Does that make sense? All right. I don't think we need to do another example. I was going to do an example with a cardioid, but I think this one is good enough. I'm just going to re-emphasize this power reducing formula. Cosine. I'm just going to write it up here. Cosine squared theta is 1 plus cosine 2 theta over 2. That's a good identity to either memorize or realize, oh, there's that identity for cosine squared theta.
And also this for sine, right?
There's a similar one for sine, I think
It's like sine of 2 theta minus 1?
it's sine of, how does that one work? It's sine of 2 theta is 2 sine theta cosine theta, I think.
Are we talking about sine squared though?
Sine squared.
No, I know there's one for cosine 2 theta as well, because I know that cosine 2 theta is equal to like
Right.
sine squared theta minus 1 or
Right.
something like that.
What, no, what was it called?
Sine squared theta equals 1 minus cosine of 2 theta.
Oh, it was 1 minus. Okay. So,
We've got them all in the front of our book.
right, they're all in the front of the book. Sine squared theta is 1 minus cosine 2 theta over 2. Yes, Anna?
Yeah.
There's a list in the very front of the book. And if there was something, if this was on often if this came up on a test, I would say find the area of such and such and cosine squared theta equals 1 plus cosine 2 theta over 2. So I would remind you guys of that one. And that would be a hint that you're probably going to need it. But just in general, these are good ones to remember because they come up often in integration. All right. Yes?
For next week's test, are we having another quiz?
We are not having another quiz.
The test starts.
The text test does start next Thursday. All right, we need to talk about a couple more things today, just quickly. The area between two curves. So the area between two polar curves. We're just going to use what we developed already to come up with an expression for the area between two polar curves. So if we have two graphs, and here are axes, and this is pi over 2, and this is 0. So we have two graphs here, and we'll call this R1, which is a function of theta, or I'm sorry, R2, which is a function of theta, and R1, which is a function of theta. Each of those is a function of theta. And we want to find the area between those curves from theta equals alpha to theta equals beta. That's the big circle minus the little circle. But we can come up with a simplified expression of this. So our area is the difference of the two integrals, like people were saying, the big circle minus the little circle. The theta integral from alpha to beta of 1/2 R2 squared d theta minus the integral from alpha to beta of 1/2 R1 squared d theta. And I can simplify this and just write the area, or the integral from alpha to beta of 1/2 R2 squared minus R1 squared, did those backwards, d theta. So just like you said, the big circle minus the little circle, but you can simplify your integral. Instead of writing two integrals, you can just combine them. And the challenge often when you're finding an area between polar curves is finding your limits of integration. And that's what I want to talk about next. Because when we're finding the area between two polar curves, often we have to find where they intersect. That will give us, we'll say, the area between this curve and this curve. We have to find what limits of integration enclose that area. Well, we can run into some problems there. So I want to talk quickly about the intersection of polar curves. So the important thing to remember, what leads to the difficulty here is that polar coordinates are not unique. We mentioned that before. Solving simultaneous equations can miss points of intersection. So in order to find all of our points, we have to graph our functions as well. So whenever we're finding points of intersection, rather than just solving simultaneous equations, graph your functions and look at the graphs. So we need to graph also. So let's look at an example of where we have a difficulty with this. So if we look at r equals 2 sine theta and r equals 2 cosine theta. Each of these is a circle. So if I graph these, I'm just going to sketch a really messy sketch here. There's one circle, and there's the other circle. This is r equals 2 sine theta, and this is r equals 2 cosine theta. If we wanted to find the area enclosed by these two curves, and we didn't graph and we just looked at simultaneous equations gives us that the tangent of theta equals 1. That's where these two are equal, where tangent theta equals 1. So theta is pi over 4. Simultaneous equations don't give us this point of intersection at the pole. Anybody have an idea of why we don't get that point at the origin from these equations? Well, let's take a look. 2 cosine theta equals 0 when theta equals pi over 2. 2 sine theta equals 0 when theta equals pi and 0. But they're different thetas. So what's happening is the curves are going through the pole at different theta values. So these theta values are not simultaneous solutions to these equations. So it's like kind of like the trick question about satellites where their orbits cross and they don't run into each other. Just because their orbits cross, they don't necessarily run into each other because they're at that point at different times. So these values of theta, the values of theta that give us 2 cosine theta equals 0 and 2 sine theta equals 0 are different values of theta, so they're not simultaneous solutions. They don't make both equations true at the same time. So the solving the simultaneous equations doesn't give us the point theta equals 0. So we have to look at our graph to find that point of intersection. If we just solve these simultaneous equations, we'd say, oh, they intersect each other at theta equals pi over 4. Now what do I do? So this is why we have to be careful, why solving simultaneous equations is not always going to give us all the solutions that we're looking for. That make sense? Okay. That's all I wanted to talk about today. So our homework.
So we just have to look at the graph basically to make sure we get all the points.
Yes. Yes.
What if it's someplace that you can't tell the input?
What's that?
What if it's at someplace where you can't tell the input?
Or you could just take that one equation, find the difference,
Right.
and then find the
So
answer that way.
right. So we would normally where it's going to give you a difficulty is at the pole, because if r equals 0 is true, at the pole 0 theta is true for any theta. So that on our previous example, that's why we were at the pole. Normally our problem point is going to be at the pole. If it's at some other point, then we'd have to figure out, then we'd have to look at the points, and maybe do some more analysis to figure out, okay, what's that point, what theta value gives that point for this curve, what theta value gives that point for the other curve, and figure it out that way.
So how did you get was the pi force just from like?
The pi force was saying that 2 sine theta equals 2 cosine theta.
So then you would graph this from 0 to pi force. That would be your.
So this point of intersection
Yeah.
is theta equals pi force.
Right. So when you were doing the.
Oh, if you were finding the area, right. So our area would go from, we do our area from 0 to pi over 4.
Even though they're not, they equal 0, that's true.
Right. For this one, I would say, okay, they're at theta equals 0. We have 0. So that's how I would go about picking the lowest one, and then we pick pi over. Then we know they intersect the pi over 4. All right. So our homework. Page 745. All right, there you go.